tutorial for Chapter 10, Section 3, titled Operations with Radical Expressions, day number 1. So let's take a look at the first type of problem we'll end up saying. It says simplify each sum or difference. And so we can do that when the radicands are the same. We can subtract and add radicals together. And since the radicands are the same here, we got 2 square roots of 11 and minus 6 square roots of 11. We'll end up with negative 4 square roots of 11. So basically we're thinking of this square root, this irrational number, is kind of like a variable. Think of it as like negative 2x, and actually not negative 2x, but just positive 2x. And so think of it as like 2x minus 6x. That would just make negative 4x. That's pretty much what we're doing. It's like combining like terms. Well, this is an irrational number. We can approximate it, but we can't say exactly what it is. That's why we're not multiplying these two values. And we can combine them together when they have the same radicand, and that's what we end up getting. So let's take a look at the next one. These are not the same radicands. So in order to do that subtraction, we need to make them the same. So if at all possible, that is, and this is possible, see how we have the square root of 9 times the square root of 7 makes 63, and the square root of 9 is 3. So we have 3 square roots of 7. We're taking that away from 4 square roots of 7, which just leaves us with 1 square root of 7, or just the square root of 7. So the key is to try to make the radicands the same. So what you could end up doing is dividing. Divide 3 into 48 here, and we'll see that 3 goes into 48 16 times. Because if it was to add, we would have to have a radicand of 3. And that's what we end up getting here when we do that division. And 3 goes into 48 again 16 times, which makes 4 square roots of 3, but then we have to multiply it by that 2. So then we get 8 square roots of 3, and that's what this first part is right here. And so over here we have already 8 square roots of 3, and we're adding these together. And so when we add these, that makes 16 square roots of 3. You're just adding up the numbers in front of the radical sign. So on this problem, we can't divide 20 into 45 on this problem, but what we can do is we can break this down to perfect squares to see if there is a common radicand or a common factor between these terms. And so I have 4 times 5, and again, what I'm trying to do is take out a perfect square that's in 20, and I saw 4 is the perfect square in 20. Over here I see 9 is the perfect square in 45, and that leaves us with 5. And this will work out, because when we go ahead and take the square root of 4, that makes 2, and we're left with the square root of 5. And over here we have the minus 2 times by 3 square roots of 5. So combining this together, this makes 6 square roots of 5 minus 6 square roots of 5, which makes 0 square roots of 5. 0 times any number, doesn't matter what it is going to end up being 0. On this next problem, we do the same sort of thing. 18 doesn't go into 32, so I'm just going to take out the perfect square. And I see 9 goes into 18. And same thing over here. So I want a square root of 2 if it's going to work out. So if you divide 2 into 32, that makes 16, and that is a perfect square. So again, I didn't break it down to 8 and 4 because that's not what I'm looking for, because I'm looking for a 2. Because I've got, on this one here, it simplifies to 5 times 3 square roots of 2, which makes 15 square roots of 2. So I want that square root of 2 from the right-hand side of the addition sign, and that's what I'm getting when I divide 2 into 32. Gives me a perfect square of 16. So the square root of 16 again is 4, and 4 times 4 makes 16. So I'm adding these together, and that makes a total of 31 square roots of 2. On the last one here, same sort of thing. I'm looking for perfect squares. I see 4 is a perfect square. That goes into 12. And over here I see 25 is the big number that goes into 75. And you see I'm left with 3 as the radicand that you can't take the square root of. And so this leaves me with 2 square roots of 3 minus 7 times 5 square roots of 3, which makes 35 square roots of 3. And I'm taking that away from 2 square roots of 3, which makes negative 33 square roots of 3. Looking at the next problem here we're simplifying each simplify each product, and so we're going to go ahead and just use the distributive property. It leaves us with the square root of 24 plus the 3 square roots of 8. Now, before I do that, I see that 8 had some perfect squares in it, so let's back up a step here. Let's go ahead and take out that perfect square. And so rather than doing that multiplication first, let's go ahead and take out the perfect square in 8. So I see that's the square root of 4, which makes 2 square roots of 2. And let's go ahead and multiply that. It'll be easier because it's already simplified. So 2 times the square root of 2 times the square root of 3 makes 2 square roots of 6. Over here it's just 2 times 3 makes 6 square roots of 2. And that's our form. Now I cannot add these because even though 2 goes into 6, you see the square root of 2 times the square root of 3 makes 6. And I can't take that square root of 3. It's not perfect. And since that's not perfect, it's not going to leave me with just a square root of 2. So I cannot combine those, so that's the way I'm going to leave them. On the next one, we're using the FOIL method here. So I've got the square root of 3 minus 4 times by the square root of 3 minus 4, because it's 2 of those, because it says it's squared. So I go ahead and use the FOIL method. Square root of 3 times the square root of 3 makes 3, because it makes the square root of 9 to start with. I'll show all those steps here. And then I do the square root of 3 times negative 4. Those are the outside terms, makes negative 4 square roots of 3. Here, the inside terms make another negative 4 square roots of 3. And the last terms make a positive 16. So I get the square root of 9 is 3. And then these two combine together because they have the same radicand. And that makes negative 8 square roots of 3 plus 16. So total, that makes 19 minus 8 square roots of 3. Looking at this last one, same sort of thing on this one, just using the FOIL method. First terms make 12 square roots of 15. So 2 times 6 makes 12, 3 times 5 makes 15. Outside terms makes negative 8 square roots of 9. So that's a perfect square there. So I'll deal with that in just a minute. Inside terms, I get a positive 6 square roots of 25. Another perfect square. And those were the inside terms. The last terms here make a negative 4 square roots of 15. So I'll go ahead and combine these two together. So that makes a 8 square roots of 15. And then the second term here makes a negative 8 times 3. This term's going to make a positive 6 times 5. So multiplying together, I get negative 24 plus 30, which makes a positive 6. And so that's going to be 6 plus 8 square roots of 15, or 8 square roots of 15 plus 6. Now typically, you like to leave the radical last, so it doesn't look like the plus 6. It doesn't get confused of being underneath the radical sign, so I'm going to write it this way. 6 plus the square root of 15. Writing it this way makes it definite that the 6 is not underneath the radical sign. Let's take a look at the last two problems that we'll see. They're going to be talking about these things called golden rectangles. And we actually watched a movie earlier on in the year, Donald Duck and Math Magic Land, and they talked about golden rectangles in that movie, and they appear frequently in nature and art. The ratio of the length to the width of a golden rectangle is this: 1 plus the square root of 5, and then is to 2. So we're going to use that ratio to help us come up with some values. And they use this because it kind of just is pleasing to the eye when you see these golden rectangles. And so here, painting is shaped as a golden rectangle. Its length is 24 centimeters. What is the width of the nearest to the nearest tenth? So notice how it says the ratio of length to width. So length to width is 1 plus the square root of 5 to 2. So the length goes along with this complex number here, and the width is this 2. So I'm going to write this as 1 plus the square root of 5 over 2. And then it says that its length is 24. So its length is 24. So it goes on top because I'm doing length on top. And what is the width? So we're not sure. So we'll put a W. And so we go ahead and cross multiply here. So we're left with W times by the 1 plus the square root of 5. And so that's being multiplied by W equals, and then 2 times 24 makes 48. And so on this other side, I'm just going to divide by the 1 plus the square root of 5 on both sides. And so what we're going to end up doing is we want to rationalize the denominator. And so they want us to, what is the length of this painting to the nearest tenth, so we're going to rationalize the denominator first. So we multiply by a conjugate. And we'll talk a little bit more about conjugates tomorrow, but it's basically going to be the opposite of the signs that we have here. So we've got, and instead of a -1, I'm going to just make it a 1 minus the square root of 5. And so they're basically kind of like differences of squares, where there's one's addition, one's subtraction. And when we go ahead and do this, it will cancel out the radicals. And so we'll see that when we go ahead and do the outside-inside terms. So on the first part here, we get 48 minus 48 square roots of 5. And then down below, we get 1 times 1 is 1. And then you see the outside terms and the inside terms are same numbers but opposite signs, so they cancel out. And the outside, the last terms, square root of 5 times square root of 5 makes the square root of 25, which just leaves us with 5. And that's a negative sign there, so let me go ahead and change that. So minus 5. So when we go ahead and do the work, we end up with 48 minus 48 square roots of 5 all over -4. So that's a rationalized denominator. Now we will be able to reduce this. So since both numbers, 48 and this one has a 48, 4 can go into both of them, we can do some division. So we can do 48 over -4, and then minus the 48, actually I'm going to put plus negative, 48 square roots of 5 over -4. So we can do some reducing there, so that makes -12 plus 12 square roots of 5. So that would be the exact form. Let's go ahead and multiply this stuff out and see what this ends up being. So pulling up the calculator, I'll go ahead and enter 12 plus, and that should be a -12, so let's fix that. Clear. So -12 plus, and then 12 times by the square root of 5. And my square root symbol is right here. And so this is what the square root of 5 is, so when I press equals, it'll do that entire calculation, and it gives me 14.8. Those are centimeters. So let's take a look at the next one. We'll go a little faster on this one. Tomato fits into a 10-inch long golden rectangle. What is the tomato's width? Okay, so we know the length is 10 inches. So we'll do 1 plus the square root of 5 over 2 equals 10 over W. We want to find that width. So we'll do the same thing. Cross multiplying here gives me W plus W square roots of 5. So actually I'm going to just write that as W times by 1 plus the square root of 5 equals 20. So I'm dividing by 1 plus the square root of 5 on both sides. And then I'll go ahead and rationalize that denominator to practice that skill. And so when I go ahead and do that, I'm left with 20 minus 20 square roots of 5 all over 1 minus 5. And so that just makes 20 minus 20 square roots of 5 over -4. Doing that division leaves me just with -5 plus 5 square roots of 5. So let's go ahead and find out what that is. And so when I clear this, I'll go -5, and then I'll do plus 5 times by the square root. So the square root of 5, and now press equals, and there it is, 6.2, rounded to the 10th place. So 6.2, and these are inches. That is our answer. So those are the problems you're going to see on tonight's assignment. Good luck.